Have you ever stopped to truly consider light? Not just flipped a switch or glanced at the sunrise, but really thought about what it is. We take it so utterly for granted. This fundamental force that shapes our world, our lives, our very perceptions. It sculpts the landscapes we admire, fuels the plants that sustain us, and allows us to connect with the world around us. It's always there, or seemingly almost always. And perhaps it's this ubiquity, this constant presence, that prevents us from fully appreciating its profound nature, and what of its counterpart, its apparent opposite. What about darkness? Is it simply the absence of light, a void where photons cease to exist? Or is it something more, something with its own intrinsic properties, its own unique presence? We use the word darkness so casually, so frequently, that we rarely pause to examine its meaning. It's the space between stars, the depths of the ocean, the inside of a cave. But is it just nothing? These questions, these fundamental inquiries into the very fabric of reality, are not just abstract, philosophical musings. They are at the heart of some of the most profound scientific discoveries of the past few centuries. And they continue to challenge us, to push the boundaries of our understanding of the universe and our place within it. Think for a moment about the last time you experienced true darkness. Not the muted gloom of a city street at night, or the dimness of a room with the curtains drawn, but genuine, unadulterated darkness. Perhaps you were camping in a remote area, far from any artificial light source. Or maybe you were exploring a cave system, venturing deep into the Earth's embrace. Remember that feeling, that profound sense of absence. Not just the absence of light, but a feeling that borders on the palpable, a weight that presses in on you. Now, contrast that with the experience of being bathed in bright sunlight, the warmth on your skin, the vibrant colors that surround you, the sense of energy and vitality that fills the air. Light is active, dynamic, a force that pushes outward. Darkness, on the other hand, feels passive, receptive, a force that draws inward. But is this perception accurate? Is darkness truly a force in its own right? Or is it simply a consequence of light's presence? This is the question we will explore, a journey that will take us from the earliest scientific inquiries into the nature of light, all the way to the cutting edge of modern physics. We'll delve into the surprising duality of light, exploring its wave-like properties and its particle nature. We'll unravel the mysteries of its speed, that cosmic speed limit that governs the interactions of everything in the universe. And we'll confront the seemingly simple but ultimately complex question: what is darkness? Is it just the absence of photons? Or does it have a more fundamental role to play in the grand cosmic tapestry? For centuries, philosophers and scientists have grappled with these questions. Aristotle believed that darkness was a substance in its own right, a tangible entity that filled the void. Later, thinkers proposed that darkness was simply the absence of light, a lack of illumination rather than an independent force. The scientific revolution of the 17th and 18th centuries brought new tools to bear on this question. Experiments with lenses and prisms revealed the intricate nature of light, demonstrating that it could be refracted, reflected, and diffracted. Scientists began to understand that light was not a single, monolithic entity, but rather a spectrum of different wavelengths, each corresponding to a different color. But even with these advances, the fundamental question of darkness remained elusive. It wasn't until the 20th century, with the advent of quantum mechanics and Einstein's theory of relativity, that we began to gain a truly deep understanding of the relationship between light and darkness. So, as we embark on this journey together, let's put aside our preconceived notions and open our minds to the possibility that the answer to this age-old question may be more surprising or profound than we ever imagined. Let's ponder the notion that perhaps darkness isn't just the absence of something, but a crucial element in the universe's endless dance, a shadow that gives form to the light, allowing it to shape the cosmos and, ultimately, define our own existence. Because, without one, the other could simply not exist. It is a universal duality, a constant rhythm that we rarely give a second thought. But maybe we should so. Let's begin at the beginning, or at least a reasonable facsimile thereof. What is light? It seems like such a simple question, doesn't it? Something we experience every waking moment, something that guides us, warms us, allows us to see the world in all its breathtaking glory. But dig a little deeper, just scratch the surface, and you'll find that light is anything but simple. A paradox, a cosmic riddle wrapped in an energetic enigma, and the key to understanding why darkness isn't a thing that moves lies in understanding the truly bizarre nature of light itself. For centuries, scientists and philosophers have grappled with this question. Is light a wave rippling through the fabric of space like water in a pond? Or is it a stream of particles, tiny bullets of energy fired from a distant source? The answer, astonishingly, is both. Light exhibits a phenomenon known as wave-particle duality. It behaves both as a wave and as a particle, depending on how we observe it. I know it sounds a little crazy, almost like something out of a science fiction novel. Imagine throwing a pebble into a still pond. You see ripples spreading outwards, right? That's a wave. It has properties like wavelength, the distance between the crests of the waves, and frequency. How many waves pass a point in a given time. Light, when behaving as a wave, also has these properties. In fact, different wavelengths of light correspond to different colors. Red light has a longer wavelength than blue light. And beyond the visible spectrum, beyond what our eyes can perceive, lie infrared, microwaves, radio waves, all part of the same electromagnetic spectrum, all behaving as waves. But then, consider a scenario where you're not looking at the ripples, but at the individual water molecules that make up the wave. These molecules are distinct, discrete packets of water. Similarly, light can also behave as a stream of these tiny packets called photons. These photons are massless particles, each carrying a specific amount of energy. The energy of a photon is directly related to its frequency. Higher frequency photons, like those of blue light, carry more energy than lower frequency photons like those of red light. This dual nature of light was dramatically demonstrated in the early 20th century through a series of experiments. Most notably, the double-slit experiment. In this experiment, light is shown through a barrier with two slits in it. Now, if light were only a particle, you'd expect to see two distinct bands of light on a screen behind the barrier, corresponding to the two slits. Think of throwing tennis balls through the slits. They'd pile up in two distinct areas. But that's not what happens. Instead, you see an interference pattern, a series of alternating bright and dark bands. This pattern is characteristic of waves. It's as if the light waves are passing through both slits simultaneously and interfering with each other, creating areas where they reinforce each other, bright bands, and areas where they cancel each other out, dark bands. The truly mind-bending part comes when you try to observe which slit each photon passes through. If you set up detectors to track the photons, something strange happens. The interference pattern disappears. The light now behaves as if it's only a particle passing through one slit or the other. The very act of observing which path the photon takes forces it to choose, to behave as a particle. It's like the light knows it's being watched and changes its behavior accordingly. Now, I know this all sounds incredibly abstract and perhaps even a little unsettling. It's one of those concepts in quantum mechanics that even physicists struggle to fully grasp. But the important takeaway is this: light is not simply a wave, and it's not simply a particle. It's something far more subtle and profound. It's a fundamental element of the universe, existing in a state of probabilistic superposition. Until we interact with it, this wave-particle duality is not just some esoteric quirk of light. It's a fundamental property of all matter. Electrons, protons, even atoms can exhibit wave-like behavior under certain circumstances. The universe, at its most fundamental level, is far stranger and more wonderful than we could ever have imagined. So, how does this all relate to the speed of light and the nature of darkness? Well, understanding that light is an electromagnetic wave, a ripple in the electromagnetic field, is crucial to understanding why it has a finite speed. Unlike a physical object traveling through space, light doesn't need a medium to propagate. It is the propagation. It's a self-sustaining wave, constantly regenerating itself as it travels through the vacuum of space. This is what allows it to travel at the mind-boggling speed of 299,792,458 meters per second. The cosmic speed limit, a speed that is intrinsically tied to the fundamental constants of the universe itself. And it's this understanding of light as a wave and a particle, as a fundamental force of nature, that sets the stage for our exploration of darkness. Because darkness, as we will soon see, is not a force. It's not a wave. It's not a particle. It's simply the absence of light. And that absence, that void, is what makes it so fascinating. So, with this foundation in place, with our understanding of light's dual nature, of darkness, light, that fundamental aspect of our universe travels at a speed so astonishing, so utterly mind-boggling, it's almost impossible to truly grasp. We call it the speed of light, denoted by the letter c. And it clocks in at a staggering 299,792,458 meters per second, roughly 186,000 per second. Try to imagine that for a moment. That's the equivalent of circling the Earth more than 7 times in a single second. It's so fast, it almost feels instantaneous in our everyday experience. But it isn't. And understanding just how not instantaneous it is unlocks some of the deepest secrets of the cosmos. For centuries, thinkers debated whether light even had a speed. Aristotle believed it traveled instantaneously. The moment a light source existed, he thought, the light reached every point in the universe. It was an intuitive idea based on our terrestrial experience. But as with so much of Aristotelian physics, it turned out to be wrong. The first successful measurement of the speed of light came in the 17th century. Thanks to the Danish astronomer Ole Rachmer, while observing the eclipses of Jupiter's moon. Ole Rachmer noticed a peculiar timing discrepancy. The eclipses appeared to occur slightly later when Earth was farther away from Jupiter in its orbit, and slightly earlier when Earth was closer. Rachmer cleverly reasoned that this difference was due to the varying distance light had to travel. When Earth was farther away, light from Io had to travel a greater distance, thus taking longer to reach us. While Rivmer's actual calculation was off due to inaccuracies in the estimated size of Earth's orbit, his methodology was groundbreaking. He proved that light did indeed have a finite speed. Later, in the 19th century, physicists like Hippolyte Fizeau and Leon Foucault used more sophisticated terrestrial experiments involving rotating toothed wheels and mirrors to obtain much more accurate measurements. These experiments confirmed Rivmer's findings and brought us closer to the precise value we know today. But the real revolution in our understanding of the speed of light came with Albert Einstein's theory of special relativity. Einstein, in his elegant and profound way, posited that the speed of light in a vacuum is constant for all observers, regardless of the motion of the light source or the observer. This seemingly simple statement has radical implications. It means that no matter how fast you are moving, you will always measure the speed of light to be the same value. See, it's a universal speed limit, an unbreakable barrier. Nothing with mass can ever reach it, let alone exceed it. Why is this? Well, as an object approaches the speed of light, its mass increases, requiring more and more energy to accelerate it further. The closer it gets to C, the more energy is needed, approaching infinity as it reaches the speed of light. It would take an infinite amount of energy to accelerate anything with mass to the speed of light, rendering it impossible. This has profound implications for interstellar travel. While science fiction often dreams of warp drives and faster than light travel, the reality is that reaching even nearby stars within a human lifetime would require speeds that are a significant fraction of the speed of light. And even then, the effects of time dilation, another consequence of special relativity, would come into play. Time would slow down for the travelers relative to those who remain on Earth. The faster they go, the more pronounced the time dilation effect becomes. So, while they might experience a relatively short journey, vast amounts of time could pass back on Earth. The constancy of the speed of light also underpins our understanding of the universe's vast distances. Light years, the unit we use to measure these immense stretches of space, are based directly on the speed of light. When we look at distant galaxies, millions or even billions of light years away, we are seeing them as they were millions or billions of years ago. The light that reaches our telescopes has been traveling for that entire time, carrying with it a snapshot of the universe's past. And what about the implications for the fundamental nature of space and time? Einstein's theory elegantly weaves these two concepts together into a single entity known as space-time. The speed of light acts as a cosmic conversion factor between space and time. It dictates how space and time are intertwined and how they are relative to different observers. The faster you move through space, the slower you move through time, and vice versa. This is not just a theoretical curiosity. It's a measurable effect that has been confirmed by numerous experiments, including those involving atomic clocks flown on airplanes. Furthermore, the speed of light is intimately connected to the electromagnetic force, one of the four fundamental forces of nature. Light itself is an electromagnetic wave, a disturbance in the electromagnetic field that propagates at, you guessed it, the speed of light. It's not just some arbitrary number. It's a fundamental constant that governs the interactions of charged particles. The implications extend even to the formation of black holes. These incredibly dense objects have such strong gravity that nothing, not even light, can escape their grasp once it crosses the event horizon. The event horizon is the boundary beyond which the escape velocity exceeds the speed of light. Inside a black hole, the very fabric of space-time is warped beyond recognition, and our understanding of physics breaks down. So, the speed of light isn't just a number. It's a key that unlocks a universe of profound concepts from the nature of space and time to the ultimate fate of stars. It's a cosmic speed limit, a universal constant, and a fundamental aspect of reality. And while we may never be able to break it, understanding it allows us to glimpse the true nature of the universe around us. It allows us to understand where everything has come from, where everything is now, and where things might be going. The more we understand the speed of light, the more our journey into the cosmos continues. Darkness, we often think of it as the opposite of light. But that's not quite right. It's not a tangible substance or an entity with its own properties. It's not something that is, but rather something that isn't. Darkness, in its purest sense, is simply the absence of light. Think of it like silence. Silence isn't a sound in itself. It's the lack of sound. Similarly, darkness is the lack of photons, those tiny packets of energy we perceive as light. To truly understand darkness, we need to first grasp how we perceive light. Our eyes, those incredible biological instruments, are designed to capture photons, specialized cells in the retina called photoreceptors specifically. Rods and cones are responsible for converting light into electrical signals that our brain can interpret. Cones are responsible for color vision and function best in bright light, while rods are more sensitive to low light levels and are responsible for our night vision. Though they don't perceive color, when light enters the eye, it strikes these photoreceptors, triggering a cascade of chemical reactions that ultimately lead to the generation of nerve impulses. These impulses travel along the optic nerve to the visual cortex, the part of the brain responsible for processing visual information. It's here, in the intricate neural networks of our brain, that we actually see light, interpret colors, and construct a visual representation of the world around us. So, what happens when there's no light? When photons cease to stimulate our photoreceptors? In that scenario, the rods and cones remain largely inactive. And in the absence of these signals, the brain interprets this as darkness. It's not receiving any information about light, so it perceives the absence of it. This brings us to a crucial point. Our perception of darkness is entirely dependent on the presence or absence of light hitting our eyes. It's a subjective experience, shaped by the way our visual system is wired. What one person perceives as darkness might be slightly different for another, depending on factors like age, health, and even the surrounding environment. Imagine stepping into a completely dark room. After being outside in bright sunlight, initially, you might feel completely blind, surrounded by absolute darkness, but gradually, your eyes adjust. The pupils dilate, allowing more light to enter, and the rods in your retina become more sensitive. This process, known as dark adaptation, allows you to see faint sources of light that were previously imperceptible. You might begin to distinguish shapes and outlines, even in what initially seemed like complete blackness. This adaptation demonstrates that even in what we perceive as darkness, there might still be a small amount of light present. Perhaps a sliver of moonlight filtering through a crack in the curtains, or a faint glow from a distant streetlight. Our eyes are remarkably sensitive and can detect even the faintest traces of light, allowing us to navigate in what would otherwise be considered total darkness. It's also important to note that our brain plays a significant role in shaping our perception of darkness. Even when there is no external light, our brain can generate its own visual experiences. This is why we can see images in our dreams, even though our eyes are closed and no light is entering them. The brain is capable of creating its own internal representations of the world, independent of external stimuli. Furthermore, our expectations and beliefs can influence how we perceive darkness. If we expect a room to be dark, we are more likely to perceive it as such, even if there is a small amount of light present. Our minds are powerful tools that can shape our sensory experiences in subtle but profound ways. Consider the concept of relative darkness. A shadow, for example, isn't truly devoid of light. It's simply an area where light is blocked, resulting in a reduction in illumination compared to the surrounding areas. The degree of darkness within a shadow depends on the amount of light that is blocked and the amount that is still able to penetrate. So, even in a shadow, there's often some level of illumination, however faint. True darkness, absolute darkness, would be a complete absence of photons. A region of space where no light waves or particles exist. This is an extremely rare occurrence, if it exists at all. Even in the deepest reaches of space, far from any stars or galaxies, there is still a faint background glow known as the cosmic microwave background radiation, a remnant of the Big Bang. This radiation, though extremely faint, represents a source of photons, albeit at very low energy levels. Therefore, the darkness we experience on Earth is almost always a relative phenomenon. It's a difference in the amount of light rather than a complete absence of it. Even on the darkest night, the stars, the moon, and even artificial light sources contribute to a small amount of illumination. So, to recap, darkness isn't a thing. It's the absence of a thing, the absence of light. Our perception of darkness is a complex interplay between our eyes, our brain, and the surrounding environment. It's a subjective experience shaped by our expectations, beliefs, and the availability of light. And while true darkness, a complete absence of photons, may be difficult to find, the relative darkness we experience on a daily basis plays a crucial role in our perception of the world and our understanding of the nature of light itself. The dance of light and darkness is a fundamental aspect of our existence, shaping our visual experiences and influencing our understanding of the universe. Let's embark on a journey back in time, not with a spaceship, but with our minds, to explore how humanity has grappled with the concept of darkness throughout history. You see, darkness wasn't always understood simply as the absence of light. Substantial, even a force in its own right. Our first stop is ancient Greece, where we encounter the philosophical musings of Aristotle. Aristotle, a towering figure in Western thought, believed that light and darkness were fundamental qualities inherent in things. He saw them as opposites, engaged in a constant struggle. He actually proposed that darkness was a positive entity that was somehow impeding light. It wasn't just not light, it was actively resisting it. Imagine a never-ending cosmic tug-of-war, with light and darkness as the opposing teams. This view permeated much of early Western thinking, influencing not only scientific inquiry, but also art, literature, and even religious beliefs. Fast forward a few centuries, and we find ourselves in the medieval period. Here, darkness took on an even more profound significance, often intertwined with religious and spiritual interpretations. Light was frequently associated with the divine, with God, with knowledge, and with good. Darkness naturally became its antithesis, linked to ignorance, evil, and the unknown. Think of the art of the time, the stark contrast between light and shadow in paintings. The way darkness was used to evoke a sense of mystery and fear. Darkness was not merely an absence, it was a powerful symbol. Interestingly, in some cultures, darkness was also revered. In certain Eastern traditions, for example, darkness was seen as the source of all creation, the primordial void from which light emerged. It was a place of potential, of mystery, and of profound wisdom. Think of the concept of the yin and yang, the complementary forces of darkness and light, neither inherently good nor bad, but essential for balance and harmony. The world has always been diverse, and there's always been competing ideas on the fundamentals of existence. Now, let's shift gears and enter the era of the scientific revolution, a time of radical shifts in how we understood the universe. As scientific tools and methodologies advanced, our understanding of both light and darkness began to evolve. In the 17th century, Isaac Newton, a giant of scientific history, made groundbreaking discoveries about the nature of light. Through his famous prism experiments, he demonstrated that white light is composed of a spectrum of colors, each with its own unique wavelength. While Newton focused primarily on light, his work laid the foundation for a more nuanced understanding of its relationship with darkness. It wasn't until the 19th century that a clearer picture of darkness began to emerge, largely thanks to the work of physicists like James Clerk Maxwell. Maxwell's equations, which unified electricity and magnetism, revealed that light is an electromagnetic wave. This understanding revolutionized our understanding of light, but also provided a new perspective on darkness. Suddenly, darkness wasn't an entity battling light. It was simply the absence of these electromagnetic waves. But the story doesn't end there. The 20th century brought with it even more revolutionary concepts, most notably Einstein's theory of relativity. Relativity fundamentally changed our understanding of space, time, and yes, even light and darkness. Einstein's famous equation, E equals mc, demonstrated the relationship between energy and mass, revealing that light, while massless, carries energy. He also posited that nothing can travel faster than the speed of light, a cosmic speed limit that has profound implications for our understanding of the universe, with relativity. The concept of darkness took on a new level of complexity. Imagine a scenario where you're traveling close to the speed of light. According to relativity, time slows down for you relative to a stationary observer. This means that the amount of light you encounter, and therefore the perception of brightness or darkness, could be different for you than for someone standing still. Spooky, isn't it? Moreover, relativity introduced the concept of black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. Black holes represent the ultimate expression, a place where light is effectively trapped and the laws of physics as we know them break down. There's still a source of ongoing scientific investigation and debate. They're also terrifying. Today, modern physics views darkness as the absence of photons, the fundamental particles of light. When there are no photons reaching our eyes or any light-detecting instrument, we perceive darkness. It's a remarkably simple explanation, yet it's taken centuries of scientific inquiry to arrive at this understanding. But even with this scientific understanding, the symbolic and philosophical significance of darkness hasn't entirely disappeared. Darkness remains a powerful symbol in art, literature, and even in our everyday language. We speak of dark secrets, dark times, and the dark side of the moon. These expressions reveal the enduring power of darkness to evoke a sense of mystery, fear, and the unknown. So, from Aristotle's cosmic tug-of-war to Einstein's light-trapping black holes, our understanding of darkness has undergone a remarkable transformation. It's a journey that reflects the evolution of human thought, our relentless quest to unravel the mysteries of the universe and our place within it. And even though we now understand darkness as the absence of light, it still holds a certain allure, a reminder of the vastness of the cosmos and the endless possibilities that lie beyond our current understanding. All right, let's tackle one of the most common misconceptions about darkness, the idea that it's a thing, a substance, or something that actively moves. Picture a room filled with light. Now, someone flips the switch, and suddenly, it's dark. What feels like happens? It feels like something rushed in, like a black tide filling the void. But that feeling is incredibly misleading. Darkness isn't a wave. It's not made of particles. It's not an entity traveling at any speed whatsoever. It simply is the absence of light. Think of it like silence. You can create silence by stopping all sounds. But silence itself isn't a thing that travels into the space. It's just the lack of sound waves. Similarly, darkness is simply the lack of photons, those tiny packets of energy that make up light. This might seem like a simple semantic difference, but it has profound implications for how we understand the universe. The belief that darkness is a tangible entity has lingered throughout history, influencing art, literature, and even scientific thought. Let's break down why darkness can't move. Movement implies a change in position over time. For something to move, it needs to have properties that can be tracked: mass, energy, momentum. Light has all of these. It's a wave and a particle carrying energy and momentum across vast distances. We can measure its speed, its frequency, its intensity. Darkness, on the other hand, is simply the lack of all of those things. It has no properties to track, no energy to measure, and no inherent position to change. It's like saying that the absence of a painting can move across a canvas. The concept just doesn't make sense. What does move is the presence or absence of light. When light is blocked or absorbed, darkness appears. A good analogy is an empty container. If you have a glass of water and you drink the water, the emptiness doesn't move into the glass, right? The water moves out, leaving emptiness behind. Emptiness itself is not a substance with its own propulsive force. It's the absence of substance. So, how does this misconception persist? It all boils down to perception. Our brains are wired to look for patterns and to interpret the world in terms of objects and their interactions. When a light source is extinguished, our senses register a rapid change from light to dark, and our brains instinctively interpret this as something entering the space. It's a cognitive shortcut, a way of quickly processing the shift in our environment. But this shortcut is, unfortunately, wrong. The sensation of darkness falling or rushing in is a construct of our minds, a trick of perception. It's not a reflection of the underlying physical reality. The change we're experiencing is the cessation of photons striking our retinas. The neurons in our eyes, no longer stimulated by light, send a different signal to our brain, and we interpret that signal as darkness. Imagine standing outside at sunset. As the sun dips below the horizon, the amount of light reaching your eyes gradually decreases. It's not that darkness is speeding towards you from the east. Rather, the source of light is being obscured by the curvature of the earth, and the number of photons streaming your way is diminishing. Think of the light in a room as the signal from a radio transmitter. The darkness is the silence you experience when the transmitter is switched off. The silence doesn't travel across the room. It's simply the absence of the radio waves. You still hear the same noises from the world around you, but the darkness allows you to focus on the world. Instead of the world being illuminated, it's important to distinguish between darkness as the absence of light and other related phenomena, such as shadows. Shadows are areas where light is blocked by an object. They're variations in light intensity, gradients between illuminated and unilluminated regions. Shadows have shapes, sizes, and positions that change depending on the position of the light source and the object casting the shadow. But even shadows are not darkness moving. They are the shifting patterns of light and obstructed light. As an object moves, it changes where the light cannot reach. But the light still has a speed, even if we can't see where it is reaching. Ultimately, understanding that darkness isn't a thing that moves challenges our intuitive understanding of the world. It requires us to think in terms of absences rather than presences. But by embracing this counterintuitive concept, we gain a deeper appreciation for the true nature of light and darkness and the fundamental laws that govern our universe. So, the next time you switch off the lights, remember that darkness isn't rushing towards you. Rather, the light is simply ceasing to be. The universe is not filling with a moving something, but rather a silence is created now. Let's delve into something truly fascinating: the profound impact of pure darkness on the human mind. We've established that darkness isn't a force, but rather the absence of light. But what happens when that absence becomes absolute? When all sensory input relating to light is stripped away? The results, as you might imagine, are, well, they're more complex than you might think. Imagine being plunged into a space where no light penetrates. A void so complete that your eyes strain for a signal they'll never receive. This isn't just turning off the lights in your bedroom. This is sensory deprivation, and it's an entirely different beast. Sensory deprivation chambers, also known as isolation tanks or float tanks, are designed to minimize all external stimuli. They're typically light-proof, soundproof, and filled with salt water heated to skin temperature, creating an environment where the body feels almost weightless. The initial experience in such an environment can be disorienting. Our brains are wired to constantly process information, to make sense of the world around us. Take away that information, and the brain doesn't simply shut down. Instead, it ramps up its own activity, searching for patterns, creating its own stimulation. One of the first things people often report in complete darkness is the emergence of phosphenes. These are those fleeting patterns of light and color that appear even when your eyes are closed. They're caused by spontaneous activity in the retina and the visual cortex, a kind of noise in the system. In the absence of external light, this internal noise becomes amplified, and those faint patterns become more vivid, more compelling. It's like your brain is trying to paint its own reality onto the blank canvas of darkness. But the effects of pure darkness go far beyond simple visual hallucinations. As the brain continues to be deprived of external input, more profound changes can occur. Time becomes distorted, losing its usual linear progression. Moments can stretch into what feels like hours, or, conversely, hours can seem to vanish in an instant. The boundaries between reality and imagination begin to blur. Some people report experiencing vivid, dreamlike states, even while consciously awake. These hypnagogic or hypnopompic experiences, the states between wakefulness and sleep, become amplified and prolonged. Memories can resurface with unusual clarity, and long-forgotten emotions can bubble to the surface. It's as if the darkness is unlocking hidden compartments in the mind, allowing subconscious thoughts and feelings to emerge. And then there are the more unsettling experiences. In prolonged darkness, some individuals report feelings of anxiety, paranoia, and even hallucinations that are less pleasant. These negative experiences are more likely to occur in people who are already prone to anxiety or who have a history of mental health issues. The lack of external stimulation can amplify existing anxieties and create a sense of disorientation and unease. The reasons for these varied responses are complex and not fully understood. Individual differences in brain chemistry, personality, traits, and past experiences all play a role. Some people find the experience of pure darkness to be profoundly relaxing and therapeutic, a chance to escape the constant demands of the modern world and reconnect with their inner selves. Others find it to be intensely unsettling and disorienting, a reminder of the fragility of our perception and the power of the mind to create its own reality. Scientists are actively exploring the potential therapeutic benefits of sensory deprivation. Studies have shown that it can be effective in treating anxiety, depression, and chronic pain. The experience of floating in darkness can induce a state of deep relaxation, reducing stress hormones and promoting a sense of well-being. It can also be used as a tool for self-discovery and personal growth, allowing individuals to confront their fears and anxieties in a safe and controlled environment. Furthermore, the altered states of consciousness experienced in sensory deprivation can enhance creativity and problem-solving abilities. By quieting the noise of the external world, the mind is free to explore new ideas and perspectives. Artists, writers, and musicians have all used sensory deprivation as a way to tap into their creative potential and break through mental blocks. However, it's important to remember that sensory deprivation is not without its risks. It's not suitable for everyone, and it should always be undertaken under the guidance of a qualified professional. Prolonged exposure to darkness can have negative psychological effects, and it's essential to be aware of the potential risks before embarking on such an experiment. But regardless of the specific effects, the experience of pure darkness highlights a fundamental truth about the human mind: that our perception of reality is deeply intertwined with our senses. We rely on light to navigate the world, to make sense of our surroundings, and to maintain our sense of orientation. Take away that light, and the mind is forced to create its own reality, a reality that can be both beautiful and terrifying, profound and unsettling. So, the next time you find yourself in a dark room, take a moment to appreciate the absence of light. Consider the profound impact that darkness can have on your mind, and remember that even in the absence of external stimulation, the human brain is capable of creating its own light, its own reality, its own unique and unforgettable experiences. And now, let's turn our thoughts towards the philosophical. There's so much more than just the presence or absence of photons. They've been intertwined with the human experience since we first huddled around a flickering fire in a dark cave. They're fundamental metaphors woven into the very fabric of our understanding of the world, ourselves, and our place within the cosmos. Think about it. Light, almost universally, represents knowledge, truth, goodness, hope, clarity. We speak of shedding light on a problem, bringing things to light, seeing the light. Enlightenment itself is, in essence, a metaphorical journey from darkness to light, a gaining of understanding that illuminates the path forward. We use the word brilliant to describe both someone intelligent and something that emits light. It's a deeply ingrained association. And what of darkness? It often symbolizes the unknown, fear, ignorance, evil, despair. We talk about being in the dark about something, a dark secret, a dark age. Darkness can be a place of hiding, a refuge for things we'd rather not confront. It's the domain of shadows, both literal and figurative. It's where monsters lurk, not always real, but always present in our anxieties. These associations aren't accidental. For millennia, our lives were governed by the rhythms of the sun. Daylight meant safety, activity, productivity. These primal fears and associations are deeply etched into our collective psyche, influencing how we perceive the world even in our modern, artificially illuminated world. But the relationship between light and darkness isn't always so clear-cut, is it? Darkness isn't simply the enemy of light. It's an essential part of the whole picture. Without darkness, there could be no light. Without shadows, there would be no depth, no contrast, no way to perceive the form and texture of the world around us. Imagine a world perpetually bathed in unrelenting light. it would be overwhelming, sterile, and ultimately meaningless. Darkness provides the canvas upon which light can paint its masterpiece. It provides the space for contemplation, for introspection. It is in the darkness that we often find the quiet. We need to connect with ourselves, to process our thoughts and emotions. It is in the darkness that we dream, that our imaginations take flight. Think of the night sky, that vast expanse of darkness punctuated by the brilliant pinpricks of stars. It's both awe-inspiring and humbling, a reminder of our own insignificance in the face of cosmic immensity. Would the stars be nearly as beautiful if there wasn't darkness to host them? Consider the cycle of day and night, the ebb and flow of light and darkness that governs so much of life on Earth. It's a rhythm that's essential for our physical and mental well-being. We need both light and darkness to thrive. We need the energy and stimulation of the day and the rest and rejuvenation of the night. To deny ourselves either is to disrupt a fundamental balance, to throw ourselves out of sync with the natural world. And just as there is darkness in the absence of light, there can also be light in the face of darkness. Think of acts of courage, compassion, and kindness that shine brightly in times of hardship and despair. These are moments when the human spirit refuses to be extinguished. When we find the strength to stand up against injustice, to offer comfort to those in need, to hold on to hope even when all seems lost. The human condition, in many ways, is a constant navigation between light and darkness. We strive for knowledge and understanding to illuminate the dark corners of our minds and the world around us. But we also grapple with our fears, our doubts, and our imperfections. We struggle to make sense of the unknown, to find meaning in the face of suffering, to reconcile the light and darkness within ourselves. Perhaps the key is to embrace both, to accept that darkness is an inherent part of life, not something to be feared or avoided, but something to be understood and even appreciated. To recognize that it is in the darkness that we often find the seeds of growth, the potential for transformation, and to remember that even in the darkest of times, there is always the possibility of light, a spark of hope, a moment of clarity, an act of kindness that can pierce through the shadows and illuminate the path forward. Like those hardy civilizations living in the shadows of dead stars. Perhaps their hardships make them more resilient, and the darkness around them causes them to cherish every moment of light. So, as we consider the nature of light and darkness, let us also consider our own relationship to them. To be sources of light in a world that can often feel dark and uncertain. And let us not be afraid to embrace the darkness within ourselves, to explore its depths, and to find the hidden treasures that may lie within. For it is in the interplay of light and darkness that we truly come to understand ourselves, our world, and our place in the vast and wondrous universe. Let's find strength in the unknown, beauty in the shadows. And let's allow the darkness to be a gentle reminder of how special the light truly is. So, we've established that darkness isn't a thing that travels, but rather the absence of light, a void, a nothingness. But the universe, ever the trickster, has a way of making even absence intriguing. Because lurking within the seemingly empty spaces of the cosmos are entities far stranger and more enigmatic than any shadow, dark matter, and dark energy. Think of it like this. Imagine you're baking a cake. You have your recipe. You carefully measure out all the ingredients: flour, sugar, eggs, butter. You mix it all together, pop it in the oven, and wait for the magic to happen. But when you take the cake out, it's heavier than it should be. It's as if someone added extra ingredients that you didn't account for. Something invisible and undetectable by your usual methods. That, in a nutshell, is the problem with the universe. We can see the stars, the galaxies, the nebulae, all the normal matter that makes up everything we can directly observe. But when we measure the gravitational effects of these objects, we find that there's not nearly enough visible matter to account for the forces at play. Galaxies are spinning far faster than they should be, given the amount of visible mass they contain. They should be flying apart. Yet, they hold together, bound by some unseen gravitational force. Something else is there. Something we can't see. Something. Dark dot, we call it dark matter. And here's the really mind-boggling part. Dark matter makes up about 85% of the total matter in the universe. All the stars, planets, and galaxies we can see are just a tiny sliver of the cosmic pie, influencing the structure and evolution of the universe in profound ways. So, what is dark matter? Well, that's the million-dollar question, isn't it? It doesn't interact with light, which is why we can't see it. It doesn't emit, absorb, or reflect any electromagnetic radiation. It's essentially invisible too. Our telescopes and detectors. Scientists have proposed various theories. One leading idea is that dark matter is made up of weakly interacting massive particles, or WIMPs. These hypothetical particles would interact with normal matter only through gravity and the weak nuclear force, making them incredibly difficult to detect. Imagine trying to catch a single raindrop in a hurricane. That's how challenging it is to find. WIMPs Other theories suggest that dark matter could be made up of axions, even lighter particles than WIMPs, or perhaps even primordial black holes. Tiny black holes formed in the early universe. The truth is, we just don't know yet, and that's what makes it so fascinating. The search for dark matter is one of the most active and exciting areas of research in modern physics. Scientists are building incredibly sensitive detectors, burying them deep underground to shield them from cosmic rays, hoping to catch a glimpse of these elusive particles. But the dark side of the universe doesn't end there. As if dark matter wasn't strange enough, we also have dark energy. If dark matter is the unseen hand that holds galaxies together, dark energy is the mysterious force that's pushing them apart. Back in the 1920s, astronomer Edwin Hubble made a groundbreaking discovery. The universe is expanding. This wasn't entirely unexpected, but what was surprising was that the expansion wasn't slowing down as gravity pulled everything back together. Instead, it was accelerating. The universe is expanding faster and faster, like a balloon being blown up at an ever-increasing rate. But what's causing this acceleration? Again, we don't know for sure. The leading explanation is dark energy, a mysterious force that permeates all of space and exerts a negative pressure, pushing everything outward. Unlike dark matter, which clumps together around galaxies, dark energy is thought to be uniformly distributed throughout the universe. And just like dark matter, dark energy makes up a significant portion of the universe, even more than dark matter, in fact. It's estimated that dark energy accounts for about 68% of the total energy density of the universe. That means that all the normal matter and dark matter we've been talking about makes up only about 32% of the universe. The vast majority is this mysterious, invisible force that we call dark energy. One possible explanation for dark energy is the cosmological constant, a term that Einstein originally introduced into his equations of general relativity to keep the universe static. That the universe was expanding. But the cosmological constant has made a comeback as a possible explanation for dark energy. It represents the energy density of empty space itself, a sort of background energy that permeates the universe. Another possibility is that dark energy is caused by a dynamic field, something that changes over time. This could be a new fundamental force of nature, or it could be a modification of gravity itself. There are many different theories, and scientists are working hard to test them and figure out what's really going on. The implications of dark energy are profound. If the expansion of the universe continues to accelerate, it could eventually lead to a big rip where the universe is torn apart by the ever-increasing expansion. Galaxies would be ripped apart, stars would be ripped apart, and eventually, even atoms would be ripped apart. It's a rather bleak scenario, but it's just one possibility. So, what can we take away from all this? Well, first of all, the universe is a lot stranger and more mysterious than we ever thought. We can only see a tiny fraction of what's actually out there. The rest is hidden, lurking in the shadows, influencing the cosmos in ways we're only just beginning to understand. Dark matter and dark energy are two of the biggest mysteries in modern physics. They challenge our understanding of gravity, of the fundamental laws of nature, and of the very nature of the universe itself. But they also offer a tremendous opportunity for discovery. As we continue to probe the depths of the cosmos, we may finally unravel the secrets of the dark universe and gain a deeper understanding of our place in it. And perhaps, in understanding the darkness, we can appreciate the light all the more. Because without the darkness, the light would have nothing to shine against. The universe is a delicate balance of opposing forces, a cosmic dance between light and darkness, matter and energy, expansion and contraction. And it's a dance that we're all a part of. Imagine light beginning its incredible journey, perhaps at the heart of a distant star, a churning, incandescent furnace fueled by nuclear fusion. This isn't just any light. It's a photon, a tiny packet of energy embarking on a voyage that could span billions of years and countless trillions of miles. It is born from unimaginable heat and pressure, a direct result of the universe's fundamental forces playing out on a grand cosmic scale. Think about the sheer energy involved. Inside that star, hydrogen atoms are being smashed together to create helium, releasing energy in the form of light and other radiation. Our photon, now free, pushes outwards, beginning its arduous climb from the star's core. This initial journey alone could take tens of thousands, even millions of years. The interior of a star is a dense, chaotic environment where photons are constantly being absorbed and re-emitted, bouncing around like a pinball in a cosmic machine. Each collision alters its path slightly, randomly, delaying its escape. But finally, it breaks free of the stellar interior and bursts out into the vacuum of space. Now, unimpeded, our photon can travel in a straight line at the speed of light, a cosmic speed limit that governs the universe. 299,792,458 meters per second. Wrap your head around that. A speed so great, it's almost impossible to truly comprehend. Our photon is now part of a vast stream of radiation, a stellar wind carrying energy and information across the interstellar void. The space between stars isn't truly empty, of course. It's filled with wisps of gas and dust, remnants of exploded stars, and the raw materials for new ones. Our photon might encounter these interstellar clouds, scattering off dust grains or being absorbed by gas molecules. If it's absorbed, its energy might be re-emitted later, perhaps at a different wavelength, changing its properties slightly, let's say. For instance, it encounters a nebula, a beautiful cloud of gas and dust illuminated by nearby stars. The nebula's atoms absorb the photon's energy and then remute it at specific wavelengths, creating those vibrant colors we see in astronomical images. The red glow of hydrogen, the blue of ionized oxygen. These are all photons that have been absorbed and re-emitted by nebulae. Each interaction telling a story about the composition and conditions of these cosmic clouds. Now, imagine our photon continues its journey, traversing the immense gulf between stars and galaxies. It might pass through regions of space that are almost perfectly empty, traveling for millions or even billions of years without encountering anything at all. This is the cosmic dark, the vast silent expanse that makes up most of the universe. Finally, after its epic journey, it approaches a planet. Our planet, Earth. The Earth is bathed in the light of our own star, the Sun, but it's also constantly bombarded by photons from distant galaxies, ancient stars, and quasars at the edge of the observable universe. Our photon might strike the Earth's atmosphere, interacting with air molecules. It could be scattered, creating the blue color of the sky. Or it might pass through the atmosphere relatively undisturbed, reaching the surface. Perhaps it lands on a leaf, where it's absorbed by a chlorophyll molecule, providing the energy for photosynthesis, the process that sustains almost all life on Earth. Or perhaps it strikes a grain of sand on a beach, warming the surface and contributing to the complex weather patterns that shape our world. And then, your eye, perhaps. The photon enters your eye, passes through the cornea and lens, and is focused onto the retina at the back of your eye. The retina is covered in photoreceptor cells, called rods and cones, which are sensitive to light. When the photon strikes one of these cells, it triggers a chemical reaction that sends an electrical signal to your brain, and that's when you see dot all that way, all that time, from the heart of a distant star to the surface of your eye. All that cosmic distance collapses into a single moment of perception. Think about it. That single photon, that tiny packet of energy, has traveled across vast distances, interacted with countless atoms and molecules, and finally triggered a cascade of events that allows you to experience the world around you. It's an almost unbelievable journey. a testament to the interconnectedness of the universe. Every time you look at the stars, every time you see the sunrise, every time you simply open your eyes and perceive the world, you're witnessing the culmination of these epic journeys. You are, in a very real sense, seeing the past. The light that reaches your eyes from distant stars has been traveling for years, decades, centuries, even millennia. You're seeing those stars as they were in the past, not as they are now. Some of those stars may have even ceased to exist by now, their light still traveling towards us, a ghostly echo of a bygone era. So, the next time you look up at the night sky, remember the incredible journey that light has taken to reach your eyes. Remember the stars, the galaxies, the nebulae, and the vast emptiness of space. And remember that you are part of this cosmic dance, a small but significant piece of the universe, connected to everything else through the exchange of light and energy. It's a humbling thought, isn't it? That the light you see has traveled for so long that it carries with it the stories of distant stars and galaxies, and that it ultimately ends its journey in your consciousness. That's the power of light, a messenger from the cosmos, bringing us information and wonder, connecting us to the vast and mysterious universe in which we live. This journey will continue long after we are gone. Light will always seek a path through space, through time, and ultimately through the universe itself. So, we've established that light travels at a mind-boggling speed, a true cosmic speed limit. But even if photons are zipping along at nearly 300,000 kilometers per second, there's a crucial distinction to be made. It's not just the speed of light that matters. It's the speed of sight. How quickly our brains can actually process the visual information that reaches our eyes. Because, let's face it, light could be delivering a masterpiece. But if our brain is still buffering, we're not going to see the whole picture. The journey from photon to perception is a surprisingly complex one. A multi-stage relay race involving a whole team of specialized cells and intricate neural pathways. When light, carrying information about the world around us, enters our eyes, it first encounters the cornea and the lens. These structures act like a focusing system, bending and directing the light onto the retina, the light-sensitive tissue at the back of the eye. Now, the retina isn't just a passive receiver. It's teeming with photoreceptor cells, the first line of defense in this visual processing pipeline. These photoreceptors come in two main flavors: rods and cones. Rods are incredibly sensitive to light, allowing us to see in dim conditions, although they don't distinguish colors very well. Think of them as the black and white specialists, enabling us to navigate a moonlit path or find our way in a darkened room. Cones, on the other hand, are responsible for our color vision and sharp detail perception. They require more light to function effectively, which is why colors seem less vibrant in low-light environments. We have 3 types of cones, each sensitive to a different range of wavelengths of light: red, green, and blue. It's the combined activity of these cones that allows us to perceive the full spectrum of colors. So that breathtaking sunset or that vibrant rainbow. All thanks to the intricate dance of these cone cells. But the story doesn't end with rods and cones absorbing the light. Once a photoreceptor absorbs a photon, it triggers a cascade of chemical reactions that ultimately generate an electrical signal. This electrical signal then travels to other cells in the retina, called bipolar cells and ganglion cells. These cells act like intermediary processors, refining the signal and preparing it for transmission to the brain. The ganglion cells are particularly important because their axons, long slender fibers, bundled together to form the optic nerve. The optic nerve is the main highway that carries visual information from the eye to the brain. Think of it as a thick cable packed with millions of individual wires, each carrying a piece of the visual puzzle. Now, here's where things get really interesting. The optic nerve doesn't send the information directly to the visual cortex, the area of the brain responsible for processing visual information. Instead, it makes a crucial pit stop at a structure called the lateral geniculate nucleus, or LGN, located in the thalamus. The LGN acts as a relay station, filtering and organizing the visual information before passing it on to the visual cortex. It's like a highly efficient switchboard operator, ensuring that the right information gets to the right place at the right time. But it's also doing some processing of its own, emphasizing certain aspects of the image, like edges and contrasts, which are crucial for object recognition. Finally, after all these detours and refinements, the visual information arrives at the visual cortex, located in the occipital lobe at the back of the brain. This is where the magic really happens. The visual cortex is organized into different areas, each specialized for processing different aspects of the visual scene. Some areas are responsible for processing color, others for motion, and still others for shape and form. These different areas work together in a hierarchical fashion, with lower-level areas processing basic features and higher-level areas integrating these features into more complex representations. It's like an assembly line, with each station adding another layer of detail to the visual image. And it's not a one-way street either. The visual cortex also receives feedback from other areas of the brain, including areas involved in memory, attention, and emotion. This feedback allows us to interpret visual information in the context of our past experiences and current goals. For example, if you see a flash of red in the forest, your brain might quickly identify it as a cardinal, drawing on your memory of what cardinals look like and triggering a feeling of appreciation. Or, if you are being chased by something, the flash of red might make you think of danger, drawing on that primal instinct to survive. So, how long does all this take? Well, estimates vary, but it's generally believed that it takes somewhere between 100 and 200 milliseconds for visual information to travel from the eye to the brain and be processed consciously. That's incredibly fast, but it's not instantaneous. There's a definite lag between the moment light hits our eyes and the moment we actually perceive what we're seeing. This lag has some interesting implications. For example, it means that what we're seeing is always slightly in the past. We're never actually seeing the present moment, only a slightly delayed version of it. However, the brain has evolved some clever mechanisms to compensate for this delay. It uses predictive coding, essentially making educated guesses about what's going to happen next based on past experience. This allows us to react quickly to changing situations, even though our perception is always a little behind. Furthermore, the speed of visual processing can vary depending on a number of factors, including the complexity of the scene, the level of attention we're paying, and even our emotional state. When we're focused and alert, our brains can process visual information more quickly and efficiently. But when we're tired or distracted, our visual processing slows down, and we may miss important details. Think about driving. When you're fully alert and paying attention to the road, you can quickly identify potential hazards and react accordingly. But when you're drowsy or distracted, your reaction time slows down, and you're more likely to get into an accident. It's not that your eyes aren't seeing the hazards. It's that your brain isn't processing the information quickly enough. And this processing speed isn't static. It can improve with training. Athletes, for example, often undergo specialized training to improve their visual processing speed and reaction time. This allows them to anticipate their opponent's moves and react more quickly, giving them a competitive edge. The speed of sight, therefore, is not just about the physics of light. It's about the intricate workings of our nervous system, the complex interplay of photoreceptor cells, neural pathways, and brain regions. It's a testament to the remarkable ability of our brains to extract meaning from the constant stream of photons that bombard our eyes, allowing us to navigate the world and interact with it in a meaningful way. It is this beautifully complex chain of events that allows us to see now. Let's dive into a concept that might initially sound like something out of science fiction, but is, in fact, at the very heart of how we understand the universe, relativity, and the intertwined nature of space-time. Think of space and time not as separate, independent entities, but as threads woven together into a single fabric, a four-dimensional continuum that shapes the cosmos. It's a bit mind-bending, I know, but stick with me. This revolutionary idea blossomed from the mind of Albert Einstein, whose theories of special and general relativity completely reshaped our understanding of gravity, light, and, crucially, the relationship between space and time. One of the key pillars of special relativity is that the speed of light in a vacuum is constant for all observers, regardless of their motion or the motion of the light source. This seemingly simple statement has profound implications. Imagine you're on a train traveling at a constant speed, and you shine a flashlight forward. Intuitively, you might think that someone standing still outside the train would see the light moving faster than it would if you were stationary. However, that's not how it works. According to special relativity, both you on the train and the observer outside will measure the speed of light to be the same. Approximately 299,792,458 meters per second. How is this possible? The answer lies in the fact that space and time are relative. That is to say, your experience of them depends on your motion. As you approach the speed of light, time slows down for you relative to a stationary observer, and distances appear to contract in the direction of your motion. These effects, known as time dilation and length contraction, become significant only at speeds approaching a substantial fraction of the speed of light. We don't notice them in our daily lives because our everyday speeds are far too slow now. How does all of this relate to darkness? Well, if nothing can travel faster than light, then darkness, being the absence of light, doesn't travel at all. It's not a thing that is subject to the limitations of the universe, so to speak. This distinction becomes crucial when we consider larger cosmic scales and the implications for our understanding of space and time. General relativity takes this a step further, introducing gravity into the equation. Einstein realized that gravity isn't just a force pulling objects together, but is instead a curvature of space-time caused by mass and energy. Imagine placing a bowling ball on a stretched rubber sheet. The bowling ball creates a dip, causing the sheet to curve. If you roll a marble nearby, it will curve towards the bowling ball, as if being pulled by a force. This is analogous to how gravity works. Massive objects warp space-time, and other objects follow the curves in space-time, which we perceive as gravity. Light, too, is affected by this curvature. Even though photons are massless, they still follow the curves in space-time created by massive objects. This is why light can be bent by gravity, a phenomenon called gravitational lensing. When light from a distant galaxy passes near a massive object, such as a galaxy cluster, the object's gravity acts like a lens, bending and distorting the light. This can create multiple images of the distant galaxy, or even stretch it into arcs or rings. Think about it. Light, the very thing that illuminates the universe and allows us to see, is itself being sculpted and manipulated by the underlying structure of space-time. And where light is absent, where darkness reigns, this warped space-time still exerts its influence, shaping the paths of anything that dares to venture near. The interplay between light and the curvature of space-time gives rise to some of the most fascinating phenomena in the universe, such as black holes. A black hole is a region of space-time where gravity is so strong that nothing, not even light, can escape. The boundary beyond which escape is impossible is called the event horizon. Once something crosses the event horizon, it is forever trapped inside the black hole. Imagine a star collapsing under its own gravity. As it shrinks, its gravity becomes increasingly intense, warping space-time more and more. Eventually, it reaches a point where space-time is so severely curved that even light cannot escape. Star has become a black hole, a point of infinite density surrounded by an invisible boundary. Black holes are not just cosmic vacuum cleaners, though. They play a crucial role in the evolution of galaxies. These behemoths, millions or even billions of times the mass of the Sun, can influence the formation of stars, the distribution of gas and dust, and the overall structure of their host galaxies. The presence of these supermassive black holes, shrouded in absolute darkness, fundamentally shapes the light we see from distant galaxies. They are the silent architects of the cosmos, their presence felt through their gravitational influence, even though they remain hidden from direct view. So, when we look out into the night sky, we are seeing a dance between light and gravity, between illumination and darkness. We are witnessing the consequences of the intertwined nature of space-time, a fabric that is constantly being stretched and warped by the presence of mass and energy. And understanding this relationship is key to unlocking the secrets of the universe. It shows us the limits of what we can see, the horizon beyond which darkness holds sway, and the profound impact that the absence of light can have on the very fabric of reality. It's a humbling thought, isn't it? Black holes. The very name evokes a sense of mystery and dread, doesn't it? These cosmic behemoths are perhaps the ultimate expression of darkness in the universe. They're not just dark objects. They're regions of space-time where gravity is so intensely strong that absolutely nothing, not even light, can escape. And if light can't escape, well, then darkness reigns supreme. Now, let's break down what that actually means, because the concept can be a bit mind-bending. We've established that light has a speed, a cosmic speed limit, and it's fast, blindingly fast. But even that incredible speed is no match for the gravitational pull of a black hole. Imagine a river so powerful that even the fastest swimmer in the world can't swim against the current. That's essentially what's happening with light and a black hole. The river is the curvature of space-time caused by the black hole's immense mass. And the swimmer is light. To understand how a black hole forms, we need to talk about stellar evolution. Stars, like our own sun, are powered by nuclear fusion. In their cores, converting hydrogen into helium and releasing tremendous amounts of energy. This energy pushes outwards, counteracting the inward pull of gravity. It's a delicate balancing act that keeps the star stable for billions of years. But eventually, the star runs out of fuel. For smaller stars, like our sun, the story ends with a whimper. They'll eventually become white dwarfs, dense remnants that slowly cool and fade away. But for much more massive stars, the ending is far more dramatic. When these stars exhaust their nuclear fuel, the core collapses under its own gravity. This collapse triggers a supernova, a colossal explosion that can outshine entire galaxies. But even the supernova isn't the end of the story. What happens after the supernova depends on the mass of the remaining core. If the core is massive enough, typically more than 3 times the mass of our sun, gravity overwhelms all other forces, and the core collapses completely, forming a black hole. So what does a black hole actually look like? Well, technically, you can't see a black hole directly because, as we've established, no light escapes from it. However, we can detect them indirectly by observing their effects on their surroundings. For instance, if a black hole is orbiting a star, it can pull matter from the star in a process called accretion. As this matter spirals towards the black hole, it heats up to millions of degrees and emits intense radiation, including X-rays. These X-rays can be detected by telescopes, giving us indirect evidence of the black hole's presence. One of the most famous images ever captured is the image of the supermassive black hole at the center of the galaxy M87. It's not a picture of Propicio, the black hole itself, but rather the shadow it casts on the surrounding hot gas. This shadow is caused by the black hole warping spacetime and bending the light around it. The image is a stunning confirmation of Einstein's theory of general relativity and provides us with the most direct evidence we have of the existence of black holes. Now, let's talk about the event horizon. The event horizon is the boundary around a black hole beyond which nothing can escape. It's often referred to as the point of no return. Once something crosses the event horizon, it's forever trapped within the black hole. The size of the event horizon depends on the mass of the black hole. The more massive the black hole, the larger its event horizon. But what happens to something that falls into a black hole? Well, according to our current understanding of physics, it gets crushed to an infinitely small point called a singularity. The singularity is the center of the black hole, where all of its mass is concentrated. It's a point of infinite density and zero volume. Oh, this is where things get really weird, because our current laws of physics break down at the singularity. We simply don't know what happens there. It's a realm where quantum mechanics and general relativity collide, and we need a new theory of quantum gravity to fully understand it. Black holes aren't just cosmic vacuum cleaners, though. They also play a crucial role in the evolution of galaxies. Supermassive black holes, millions or even billions of times the mass of our Sun, reside at the centers of most galaxies, including our own Milky Way. These behemoths can influence the formation and evolution of their host galaxies by regulating star formation and driving powerful jets of particles and radiation. These jets, launched from the vicinity of the black hole, can extend for millions of light years and can heat up the surrounding gas, preventing it from cooling and forming new stars. In this way, supermassive black holes can act as a sort of cosmic thermostat, regulating the growth of their host galaxies. So, black holes are not just about darkness and destruction. They're also about creation and regulation. They're a fundamental part of the universe, shaping the structure of galaxies and influencing the evolution of stars. They're a reminder that even in the darkest corners of the cosmos, there is always something new and amazing to be discovered. And as we continue to study these enigmatic objects, we'll undoubtedly uncover even more secrets about the nature of gravity, space-time, and the universe itself. They are, in a sense, the ultimate embodiment of the dance between light and darkness, a testament to the awe-inspiring power and mystery of the cosmos. They are the ultimate example of a place where light cannot escape and darkness reigns supreme. Now, let's turn our gaze back, far back, further than galaxies, further than stars, further than anything we can readily perceive. We're going back to the very beginning, or at least as close as we can get. We're going back to the first. Light. Imagine, if you will, an infinitesimally small point, hotter and denser than anything we can fathom. This is the singularity, the theoretical starting point of our universe. Then, in a cataclysmic event known as the Big Bang, this singularity expands outward at an unimaginable rate. It isn't an explosion in space, but rather an explosion of space itself. For the first few moments, the universe is an opaque soup of incredibly hot plasma. Energy and matter are interchangeable, constantly colliding and annihilating each other in a chaotic dance. It's a period of rapid inflation where the universe expands exponentially, smoothing out any initial irregularities. This early universe is far too hot for even atoms to form. Imagine a pressure cooker heated to trillions of degrees. Nothing complex can survive in that environment. But as the universe expands, it cools. And as it cools, the fundamental particles, quarks, leptons, bosons, begin to take shape. These particles then combine to form protons and neutrons, the building blocks of atomic nuclei. This is the era of nucleosynthesis, when the light elements, like hydrogen and helium, are forged in the furnace of the early universe. Still, light cannot travel freely. The universe is still dense with charged particles, constantly scattering photons, trapping them in a cosmic fog. It's like trying to see through a thick cloud of smoke. Light is there, but it can't escape. Rains. Then something remarkable happens. Around 380,000 years after the Big Bang, the universe cools enough for electrons to combine with atomic nuclei, forming neutral atoms. This process is called recombination, although a more accurate name would be combination, as it was the first time electrons and nuclei had combined. And here's the key. Neutral atoms are far less effective at scattering photons than charged particles. Suddenly, the universe becomes transparent. This is the moment we call the surface of last scattering, or the epoch of recombination. The universe, for the first time, is bathed in light. This first light, often referred to as the cosmic microwave background, or CMB, is a faint afterglow of the Big Bang. It's the oldest light in the universe, a snapshot of the cosmos in its infancy. It's a testament to the incredible journey light has taken from the primordial soup to our telescopes. Think of it like this. Imagine a foghorn sounding in a dense fog. You can't see the source of the sound, but you can hear its echo bouncing off the fog particles. Similarly, we can't see the Big Bang directly, but we can detect the echo of its light, the CMB permeating the entire universe. Now, this isn't your typical light. It's not the kind of light that illuminates our world, the kind that allows us to see colors and textures. Instead, the CMB is in the microwave portion of the electromagnetic spectrum, invisible to the naked eye. It's a faint, uniform glow with only minuscule temperature fluctuations, but these tiny fluctuations are incredibly important. They represent the seeds of all the structures we see in the universe today: galaxies, stars, and planets. They're like the faint ripples in a pond that eventually coalesce into waves. These variations in density imprinted on the CMB are the result of quantum fluctuations in the very early universe. Amplified by inflation, scientists have meticulously mapped the CMB using sophisticated telescopes like the Planck satellite and the Wilkinson Microwave Anisotropy Probe (WMAP). These maps reveal a wealth of information about the age, composition, and geometry of the universe. They provide strong evidence for the Big Bang Theory and allow us to test our cosmological models with unprecedented precision. The CMB is not just a relic of the past. It's a powerful tool for understanding the present and future of the universe. By studying the CMB, we can learn about the nature of dark matter and dark energy, the mysterious components that make up the vast majority of the universe's mass energy. Content. Consider this: when we observe the CMB, we are looking back in time to a point when the universe was only 380,000 years old. That's like looking at a photograph of a baby that's just a few days old. From that single image, we can infer a lot about the baby's future development. Similarly, from the CMB, we can infer a lot about the future evolution of the universe. It's a humbling experience to contemplate the vastness of space and time and our place within it. The light from the CMB has traveled for billions of years to reach us, carrying with it a message from the dawn of creation. It's a reminder that we are all connected to the universe in a profound way, that we are all made of star stuff, as Carl Sagan so eloquently put it, and perhaps the stuff from even before the stars. So, the next time you look up at the night sky, remember the first light. Remember the CMB, the faint afterglow of the Big Bang, permeating the entire cosmos. It's a reminder that even in the deepest darkness, there is always light waiting to be discovered. A light that tells the story of the universe, a story that is still being written, a story that includes us. And as we continue to explore the cosmos, we'll undoubtedly uncover even more secrets about the first light and the universe it illuminated. We are always learning, always pushing the boundaries of our understanding, and that, in itself, is a remarkable journey. A journey fueled by curiosity, driven by a thirst for knowledge, and illuminated by the light of discovery. Began with the Big Bang and continues to this day. Since the dawn of civilization, artificial light has been a transformative force, reshaping our lives, our societies, and even our planet. From flickering oil lamps to the ubiquitous glow of LEDs, humanity's quest to conquer darkness has been relentless. But this victory over the night comes with a cost. One we are only beginning to fully understand. Think back to the ancient world. The setting sun dictated the rhythm of life. Activities were confined to daylight hours. The night was a realm of mystery, fear, and limited possibilities. The invention of fire was, of course, the first major step, pushing back against the darkness. With the comforting warmth and light of a controlled flame, torches, oil lamps, and candles followed, allowing our ancestors to extend their day, gather together after sunset, and begin to develop more complex social structures. Imagine the stories told around a crackling fire, the knowledge passed down, the bonds forged in the shared experience of artificial light. Over centuries, these light sources evolved, becoming more efficient and more accessible. Gas lamps illuminated city streets in the 19th century, transforming urban life and ushering in a new era of safety and commerce. Suddenly, the night was no longer the exclusive domain of criminals and creatures of the imagination. It became a time for entertainment, for work, and for social interaction. The world opened up, and the pace of life accelerated. But the true revolution came with the invention of the incandescent light bulb by Thomas Edison. This single invention, more than any other, defined the modern age. Suddenly, light was cheap, readily available, and easily controlled. Homes were illuminated, factories hummed through the night, and cities became dazzling displays of electric brilliance. The world had never been brighter. Today, we are surrounded by artificial light. It permeates every aspect of our lives. The screens we stare at for hours each day to the streetlights that guide our way home. From the headlights of passing cars to the illuminated advertisements that bombard our senses, we are constantly bathed in artificial light. LEDs, compact fluorescent lamps, CFLs, and halogen bulbs have replaced the incandescent bulb, offering greater energy, efficiency, and longer lifespans. But the fundamental impact remains the same. We have conquered the night. But what are the consequences of this conquest? What have we lost in our relentless pursuit of illumination? The answer, it turns out, is more complex and far-reaching than we might initially imagine. One of the most significant consequences is light pollution. This refers to the excessive or misdirected artificial light that illuminates the night sky, obscuring the stars and disrupting natural ecosystems. Light pollution is a growing problem, particularly in urban areas. It not only diminishes our ability to appreciate the beauty of the night sky, but also has a profound impact on wildlife. Many species of animals rely on natural patterns of light and darkness for navigation, foraging, and reproduction. Artificial light can disrupt these patterns, leading to confusion, disorientation, and even death. Migratory birds, for example, are often attracted to brightly lit buildings, causing them to collide with windows and towers. Sea turtles, which rely on the moon's reflection on the water to find their way to the ocean after hatching, can become disoriented by artificial lights and wander inland, where they are vulnerable to predators. Nocturnal insects, drawn to artificial lights, can be trapped in light fixtures or exhaust themselves flying around them, disrupting their natural feeding and mating behaviors. Even plant life is affected by light pollution. Artificial light can interfere with the natural rhythms of plant growth, delaying dormancy in the fall and causing premature budding in the spring. This can make plants more vulnerable to frost damage and disrupt the delicate balance of ecosystems beyond. The environmental impact. Artificial light also has a significant effect on human health. Our bodies are naturally attuned to the rhythms of the sun, with our sleep-wake cycles regulated by the hormone melatonin, which is produced in darkness. Exposure to artificial light, especially blue light emitted by electronic devices, can suppress melatonin production, disrupting our sleep patterns and leading to a variety of health problems. Studies have shown that exposure to artificial light at night can increase the risk of obesity, diabetes, cardiovascular disease, and even certain types of cancer. It can also exacerbate mental health issues such as depression and anxiety. The constant barrage of artificial light can disrupt our circadian rhythms, leading to fatigue, irritability, and decreased cognitive function. Fortunately, there are steps we can take to mitigate the negative consequences of artificial light. This can be achieved by using shielded light fixtures that direct light downwards, reducing the amount of light that escapes into the sky. Using lower intensity lights and turning off lights when they are not needed can also make a significant difference. Choosing warm-toned light bulbs, which emit less blue light, can also help to minimize the impact on melatonin production. On a personal level, we can take steps to reduce our exposure to artificial light at night. This includes turning off electronic devices at least an hour before bedtime, using blue light filters on our screens, and creating a dark and quiet sleep environment. Spending time outdoors during the day can also help to regulate our circadian rhythms and improve our sleep quality. Ultimately, the key is to find a balance between the benefits of artificial light and the need to protect our environment and our health. Artificial light has undoubtedly transformed our world for the better. But it is important to use it responsibly and to be mindful of its potential consequences. By embracing more sustainable lighting practices and making conscious choices about our exposure to artificial light, we can ensure that future generations will be able to enjoy the benefits of illumination without sacrificing the beauty of the night sky or the health of our planet. The dance of light and darkness is a delicate one, and it is our responsibility to ensure that it continues in harmony. We've painted a picture of a world bathed in the artificial glow of our cities, and it's a beautiful picture in a way, a testament to human ingenuity and our drive to conquer the darkness. But like any conquest, this one has its casualties. And in this case, the casualties are the environment, our wildlife, and even our own health. We're going to explore the impact of light pollution, the often unseen consequences of our seemingly harmless desire to illuminate the night dot. So, what exactly is light pollution? It's more than just a little extra brightness. It's any adverse effect caused by artificial light, including sky glow, light trespass, glare, and clutter. Think of sky glow as that hazy dome of light you see above cities at night, obscuring the stars. Light trespass is when light shines where it isn't intended or needed, like your neighbor's security light beaming into your bedroom window. Glare is excessive brightness that causes discomfort or reduces visibility, such as the blinding headlights of oncoming traffic and clutter. That's the confusing and excessive grouping of lights, like a strip mall parking lot that feels brighter than daylight. These different forms of light pollution aren't just aesthetic nuisances. They have profound ecological consequences. For countless species, darkness is a critical part of their natural habitat. It governs their behavior, their reproduction, and their survival. Think about sea turtles, for example. Newly hatched sea turtles instinctively move toward the brightest horizon, which, under natural conditions, would be the open ocean reflected by the moon and starlight. But coastal light pollution disorients them, drawing them inland towards streets and away from the sea. Sadly, many of these hatchlings die from exhaustion, dehydration, or being hit by cars, never even getting a chance to begin their lives. Migratory birds are also heavily impacted. They rely on the stars for navigation during their long journeys. Artificial lights can confuse them, causing them to fly off course, collide with buildings, or circle endlessly until they drop from exhaustion. Imagine being a bird navigating by an ancient map etched into your very being, only to find that map obscured by an alien artificial glow. It's a disruption on a scale that's difficult to comprehend. Even insects, the unsung heroes of our ecosystems, are vulnerable to light pollution. Moths, famously drawn to flames, are attracted to artificial lights, often with fatal consequences. This disrupts their natural pollination activities and impacts the food chain, affecting the animals that depend on them. And it's not just moths. Many nocturnal insects are attracted to lights, leading to their exhaustion and death, and altering the delicate balance of insect populations within ecosystems. It is a silent, cascading effect rippling through the web of life. The consequences extend beyond the animal kingdom. Plants, too, are affected. And reproductive success. This, in turn, can affect the entire ecosystem, as plants form the foundation of many food webs. Imagine trees budding too early in the spring, only to be damaged by a late frost. It's a disruption that can have far-reaching consequences, but the impact of light pollution isn't limited to the environment. It also affects us as humans. Our bodies are finely tuned to the natural rhythms of day and night, governed by the hormone melatonin. Melatonin plays a vital role in regulating our sleep cycles, boosting our immune system, and protecting us from certain types of cancer. Exposure to artificial light at night suppresses melatonin production, disrupting our sleep patterns and potentially increasing our risk of health problems. Studies have linked light pollution to a variety of health issues, including sleep disorders, depression, obesity, and even an increased risk of certain cancers. It's a subtle, insidious threat, quietly undermining our well-being. Think about it. How often do you truly experience a night sky filled with stars? For many of us, it's a rare treat, reserved for trips to remote areas far from the city lights. We've lost our connection to the natural night, and it's taking a toll. And it's not just our physical health that's affected. Light pollution also impacts our mental and emotional well-being. The night sky has been a source of wonder and inspiration for humanity since the dawn of time. It's a canvas upon which we've projected our myths, our dreams, and our deepest fears. When we lose the ability to see the stars, we lose a part of ourselves. We lose a sense of connection to the universe and to our place within it. Imagine trying to write poetry without the moon, or compose music without the hush of a dark, star-filled night. A lot of our most profound art has risen from the darkness. Fortunately, the news isn't all doom and gloom. There are things we can do to mitigate the effects of light pollution. Simple solutions, like using shielded light fixtures that direct light downwards, rather than upwards and outwards, can make a big difference. Switching to lower intensity lights and using timers or motion sensors to turn off lights when they're not needed can also help. And supporting local initiatives to reduce light pollution is crucial. Dark sky parks and reserves are becoming increasingly popular, offering havens of natural darkness where people can reconnect with the night sky. These areas serve as important reminders of what we're losing and what we can still protect. Imagine a place where the Milky Way stretches across the sky like a river of light, where the stars are so bright they cast shadows. These places exist, and they're worth preserving, ultimately. Reducing light pollution is about finding a balance between our need for illumination and our need for darkness. It's about being mindful of the impact our actions have on the environment and on our own health. It's about recognizing that the night sky is a precious resource, one that deserves our protection. So, next time you look up at the night sky, or rather, can't look up at the night sky, take a moment to consider the impact of light pollution. Think about the sea turtles, the birds, the insects, the plants, and even ourselves. Think about the darkness that we're losing and what we can do to bring it back. It's a challenge, but it's one that's worth taking on. Because, in the end, the darkness is not our enemy. It's a vital part of our world, and it deserves our respect. We've conquered the night with our lights, but we've inadvertently pushed aside an essential piece of our planet. Perhaps now we can begin to reclaim it. Darkness, it's more than just the absence of light. It's a canvas upon which we've projected our deepest fears, our grandest aspirations, and the very essence of the unknown for millennia. From the flickering shadows of ancient cave paintings to the stark contrasts of modern art, darkness has been a potent symbol, a constant companion in our artistic and cultural endeavors. Think back to the earliest days of humanity. Imagine huddled around a crackling fire, the only source of light in a world shrouded in impenetrable blackness. Those dancing flames cast elongated shadows on the cave walls, transforming them into a living theater. For our ancestors, these shadows weren't just a consequence of light. They were imbued with power, with mystery, with the potential for both good and evil. The cave paintings themselves, often depicting animals and hunting scenes, were born from this interplay of light and darkness. They were attempts to capture the spirit of the hunt, to invoke the favor of the gods, and to ward off the dangers lurking in the night. Darkness, in this context, was both a source of fear and a source of inspiration. It was the domain of the unknown, the realm of the spirits, and the birthplace of art. Fast forward to ancient civilizations. In Egyptian mythology, darkness was personified by Apep, the serpent of chaos, forever battling the sun god Ra. Every night, Ra would descend into the underworld, a realm of darkness and uncertainty, only to emerge triumphant in the morning, bringing light and order back to the world. This constant struggle between light and darkness became a powerful metaphor for the cycle of life and death, the eternal battle between good and evil, and the enduring hope for rebirth and renewal. Similarly, in Greek mythology, Hades ruled the underworld, a realm of shadows and eternal night. While not necessarily evil, Hades represented the inevitability of death, the ultimate darkness that awaits us all. His realm was a place of somber reflection, a reminder of our mortality and the fleeting nature of life. The influence of darkness extends far beyond mythology. In art, the use of chiaroscuro, the dramatic contrast between light and dark, became a hallmark of Renaissance and Baroque masters. Artists like Caravaggio and Rembrandt used darkness not merely as a backdrop, but as an active force shaping the composition, highlighting key elements, and creating a sense of drama and emotional intensity. Think of Caravaggio's asterisk, the entombment of Christ's asterisk. The figures emerge from a deep, almost palpable darkness, their faces illuminated by a stark light that emphasizes their grief and the weight of their loss. The darkness itself becomes a character in the scene, a symbol of death and despair. Rembrandt, too, was a master of light and shadow, using darkness to create a sense of intimacy and psychological depth. His portraits are often bathed in a soft, diffused light, with large areas of the canvas shrouded in darkness. This technique allows him to focus our attention on the subject's face, revealing their inner thoughts and emotions. The darkness around them becomes a protective cocoon, shielding them from the harsh realities of the world. In literature, darkness has served as a powerful symbol of ignorance, despair, and the unknown. Joseph Conrad's Heart of Darkness explores the darkest aspects of human nature, using the physical darkness of the African jungle as a metaphor for the moral darkness that can consume us. The protagonist, Marlowe, journeys into the heart of the Congo, encountering brutality, exploitation, and the terrifying figure of Kurtz, a man who has succumbed to the darkness within. The darkness of the jungle mirrors the darkness of the human soul, a place where reason and morality can easily be lost. Shakespeare, of course, explored the themes of light and darkness with unparalleled depth and nuance. In Hamlet, the prince's inner turmoil is often expressed through images of darkness and decay. Longing for an escape from the darkness of his grief and the corruption of the court, Lady Macbeth, driven by ambition and guilt, famously cries out, "Out, damned spot! Out, I say!" desperately trying to wash away the metaphorical darkness of her sin. Even in music, darkness plays a significant role. From the somber melodies of funeral marches to the brooding intensity of heavy metal, darkness can evoke a wide range of emotions. The blues, born from the struggles of African Americans in the Jim Crow South, often uses dark imagery to express feelings of pain, loss, and oppression. The minor key, with its inherent sense of sadness and melancholy, becomes the musical equivalent of darkness, reflecting the hardships and injustices faced by the community. Moving into modern times, darkness continues to be a powerful source of inspiration for artists and creatives. In film noir, the shadows of urban landscapes become metaphors for moral ambiguity and the corrupting influence of power. The characters in these films often operate in a world of gray areas where it's difficult to distinguish between good and evil. The darkness of the alleys and back streets reflects the darkness of their souls. In contemporary art, darkness can be used to explore themes of alienation, isolation, and the search for meaning in a chaotic world. Artists may use dark colors, stark contrasts, or unsettling imagery to create a sense of unease and challenge the viewer's perceptions. The absence of light becomes a way to confront the uncomfortable truths about ourselves and the world around us. Consider the work of Anish Kapoor, specifically his use of vantablack, one of the darkest substances known. When applied to a sculpture, vantablack absorbs almost all light, creating an illusion of infinite depth, a void that seems to swallow everything whole. This darkness is not merely aesthetic. It's a metaphysical experience, a confrontation with the abyss, the void that lies at the heart of existence. So, as we can see, darkness is far more than just the absence of light. A symbol, a metaphor, a source of inspiration, and a powerful tool for artists and creators across all disciplines. It represents the unknown, the mysterious, the hidden aspects of ourselves and the world around us. It challenges us to confront our fears, to explore our inner depths, and to find meaning in the face of uncertainty. It reminds us that even in the darkest of times, there is always the potential for light to emerge, for hope to prevail, and for art to illuminate our path forward. And as we continue our journey through this exploration of light and darkness, let us not forget the profound impact that darkness has had on shaping our culture, our art, and our understanding of ourselves. All right, let's dim the light a little further and delve into the fascinating world of shadows, those ever-present companions to light. We often take them for granted, but shadows are actually a beautiful demonstration of how light interacts with the world around us. They're not some mysterious, dark substance rushing to fill a void. Instead, they're simply the absence of light. In a specific area, an area where something is blocking its path. Think of it like this. Light travels in straight lines, zipping through space until it encounters an obstacle. This obstacle could be anything: a tiny speck of dust, a towering mountain, or even you and me. When light hits an object, several things can happen. It can be absorbed, reflected, or transmitted, meaning it passes right through. The dance between these processes is what gives objects their color and creates those captivating shadows. Let's start with absorption. Different materials absorb different wavelengths of light. A black shirt, for example, absorbs almost all the visible light that hits it. That's why it appears black to our eyes. The light energy that's absorbed is converted into heat, which is why wearing black on a sunny day can make you feel warmer. Conversely, a white shirt reflects almost all the visible light, which is why it stays cooler. Now, reflection is what allows us to see objects in the first place. When light bounces off an object and enters our eyes, our brains interpret that light and create an image. The surface of an object determines how light is reflected. A smooth surface, like a mirror, reflects light in a uniform way, creating a clear reflection. A rough surface, on the other hand, scatters light in many directions, creating a diffuse reflection. This is why you can see your reflection in a still lake, but not in a choppy ocean. And finally, we have transmission. This is when light passes through an object. Clear glass, for example, transmits most of the light that hits it, allowing us to see what's on the other side. But even transparent materials can absorb and reflect some light. If they didn't, glass windows would be invisible. So, how do these interactions create shadows? Well, when an object blocks light, it prevents it from reaching the area behind it. This area becomes a shadow, a region where the light intensity is reduced compared to the surrounding area. The shape of the shadow is determined by the shape of the object and the angle of the light source. The type of shadow we see also depends on the nature of the light source. A point source of light, like a small, unfrosted light bulb, creates a sharp, well-defined shadow. This is because the light rays are traveling in a straight line from a single point. However, most light sources are not point sources. They have some size and emit light from multiple points. This creates two distinct parts to a shadow: the umbra and the penumbra. The umbra is the dark, central part of the shadow where the light source is completely blocked. If you were standing within the umbra, you wouldn't be able to see any part of the light source. The penumbra, on the other hand, is the lighter, fuzzy area around the umbra where the light source is only partially blocked. From within the penumbra, you'd be able to see part of the light source, but it would be dimmer than normal. Think of it like this. Imagine you're standing in front of a large window with the sun shining through. If you hold your hand up close to the window, you'll create a sharp, dark shadow on the wall behind you. This is the umbra. But if you move your hand further away from the window, the shadow will become larger and fuzzier. The fuzzy area around the dark center is the penumbra. The size and shape of the umbra and penumbra depend on the size of the light source and the distance between the object and the surface where the shadow is cast. A larger light source will create a larger penumbra, while a smaller light source will create a smaller penumbra and a sharper umbra. Shadows also play a crucial role in how we perceive depth and shape. Our brains use shadows to interpret the three-dimensional structure of objects. Think about a simple sphere. Without shadows, it would just look like a flat circle. But with shadows, we can see its curvature and understand that it's a three-dimensional object. Artists use this principle to create realistic drawings and paintings, carefully manipulating shadows to create the illusion of depth. Even the color of light affects the appearance of shadows. If you shine a red light on an object, the shadows will appear to be tinged with blue-green, the complementary color of red. This is because the red light is being blocked, allowing other wavelengths of light to become more visible in the shadow. So, the next time you see a shadow, take a moment to appreciate the complex interplay of light and matter that creates it. It's a reminder that even in the absence of light, there's a fascinating story to be told, a story of absorption, reflection, and transmission. And perhaps it is in those stories that we begin to understand the nature of our own experience, the contrast of light and dark, joy and sorrow, presence and absence. It's all part of the grand cosmic dance. Now, let's turn our attention to where light and darkness play, perhaps, their most crucial role. Within the delicate dance of life itself, we often think of physics and biology as separate disciplines, but light, in its magnificent duality, bridges the gap, becoming the very foundation upon which life flourishes. First, let's consider photosynthesis, that wondrous process by which plants, algae, and some bacteria harness the energy of sunlight to convert carbon dioxide and water into glucose and oxygen. Think about that for a moment. Light, that ephemeral wave, an energetic particle, is the engine that drives the entire terrestrial food web. Photons, those tiny packets of light energy, are absorbed by chlorophyll, the pigment that gives plants their verdant hue. This absorbed light kicks off a cascade of chemical reactions, a sort of molecular ballet fueled by the sun. Without light, photosynthesis grinds to a halt. So plants, starved of their energy source, wither and die. And the ripple effect spreads throughout the ecosystem. Herbivores lose their food source, carnivores lose their prey, and the entire delicate balance collapses. The very air we breathe, enriched by the oxygen produced during photosynthesis, would become progressively depleted. So, the next time you see a plant basking in the sunlight, remember that you are witnessing a fundamental act of creation, act powered by the ceaseless flow of photons. But the story of light and biology doesn't end with photosynthesis. We can turn to the fascinating world of bioluminescence. Here, life itself becomes a source of light. Fireflies blinking in the twilight, deep-sea creatures glowing in the abyssal depths. These are just a few examples of the astonishing diversity of bioluminescent organisms. Unlike incandescence, which generates light through heat, bioluminescence is a chemical reaction. A molecule called luciferin reacts with oxygen, often catalyzed by an enzyme called luciferase, producing a cool, gentle glow. The reasons for bioluminescence are as varied as the creatures that produce it. Some organisms use it for camouflage, blending into the faint, downwelling light of the ocean depths. Others use it to attract prey, luring unsuspecting victims into their deadly embrace. Still, others use it for communication, signaling to potential mate or warning off rivals. In the inky blackness of the deep ocean, bioluminescence is a language of light, a silent conversation unfolding in the darkness. Consider the anglerfish, a truly bizarre and fascinating creature. It dangles a bioluminescent lure in front of its mouth, enticing smaller fish to come closer. Unsuspecting, these smaller fish swim towards the light, only to be quickly devoured. A stark illustration of the role light can play in the drama of survival. Or think of the countless species of bioluminescent bacteria that light up the ocean surface in shimmering displays. These displays, often triggered by movement, can be so intense that they can be seen from space. A testament to the collective power of these tiny organisms, beyond photosynthesis and bioluminescence. Light also plays a crucial role in regulating the internal rhythms of life. Most organisms, from single-celled bacteria to complex mammals, possess internal biological clocks, often referred to as circadian rhythms. These clocks, with a cycle of roughly 24 hours, regulate a wide range of physiological processes, including sleep-wake cycles, hormone production, and body temperature. And what synchronizes these internal clocks? Light. Specialized cells in the retina of the eye detect light and transmit signals to the brain, specifically to a region called the suprachiasmatic nucleus, or SCN. The SCN is the master pacemaker of the circadian system, and it uses light cues to reset the body's internal clock each day. Think about jet lag. When you travel across time zones, your body's internal clock becomes misaligned with the external environment. The light-dark cycle is out of sync with your usual routine, and it takes time for your SCN to adjust. This misalignment can lead to fatigue, insomnia, and a host of other unpleasant symptoms. It is your body struggling to adjust its inner sense of time and place, even the changing seasons, governed by the variations in day length throughout the year, influence our biology. In many animals, seasonal changes in light exposure trigger changes in behavior, such as migration, hibernation, and reproduction. In humans, seasonal affective disorder, or SAD, is a condition characterized by symptoms of depression that occur during the winter months when daylight hours are shorter. These symptoms are thought to be related to disruptions in the circadian system caused by reduced light exposure. Light, therefore, is not just an external stimulus. It is an integral part of our internal machinery. It shapes our behavior, regulates our physiology, and influences our mood. It is a constant companion, guiding us through the cycles of day and night. The rhythms of the seasons and the intricate dance of life itself. In essence, life has evolved to not only exist with light, but to harness it and use it in amazing and surprising ways. From the macroscopic global scale of plant life to the microscopic world of cellular timekeepers, light is a conductor of life. Even the very darkness, that quiet, subtle contrast, serves an important role in calibrating our inner clocks and protecting life where the sun's rays can't reach. The human eye, magnificent as it is limited. It's a receiver tuned to a narrow band of the electromagnetic spectrum we call visible light. But what if we could expand our perception, shatter those limitations, and truly see in the dark, and even beyond the conventional light spectrum? This isn't just science fiction. It's an area of intense research and development, pushing the boundaries of physics and engineering to create technologies that grant us extraordinary vision. One of the most established methods, of course, is thermal imaging. This technology detects infrared radiation, the heat emitted by objects. Everything above absolute zero radiates infrared, and the hotter an object, the more it radiates. Thermal cameras convert this infrared radiation into a visible image, allowing us to see heat signatures in complete darkness. Think of search and rescue operations, finding lost individuals by detecting their body heat against a cold environment, or consider building inspections, identifying areas of heat loss due to poor insulation. Thermal imaging has become indispensable across countless industries. It's a testament to our ability to extend our senses beyond their natural capabilities. But what about seeing through obstacles, not just detecting heat? That's where terahertz imaging comes in. Terahertz radiation, located between microwaves and infrared on the electromagnetic spectrum, has the unique property of being able to penetrate many materials that are opaque to visible light, such as clothing, paper, and certain plastics, while still an emerging technology. Terahertz imaging holds immense potential for security screening, allowing us to detect concealed weapons or contraband without invasive searches. It could also revolutionize medical imaging, offering a nanizing alternative to X-rays for detecting tumors and other abnormalities. The challenge lies in developing compact and affordable terahertz sources and detectors. But the progress is rapid and the future looks bright. Even when looking into darkness, beyond these established and emerging technologies, researchers are exploring even more exotic approaches. Consider the realm of quantum imaging. This utilizes the bizarre properties of quantum entanglement to create images with unprecedented sensitivity. One technique, known as ghost imaging, involves entangling two photons, directing one towards the object being imaged and the other towards a detector. Even though the detector never directly interacts with the object, it can still create an image based on the correlations between the entangled photons. This allows for imaging in extremely low light conditions, potentially revealing details that would otherwise be invisible. Another fascinating avenue of exploration is the development of metamaterials. These are artificial materials engineered to have properties not found in nature. By carefully designing the structure of metamaterials at the sub-wavelength scale, scientists can manipulate the way light interacts with them, bending and focusing light in unusual ways. Imagine a metamaterial lens that can focus light beyond the diffraction limit, allowing us to see details smaller than the wavelength of light itself. Or a metamaterial cloak that can render objects invisible by bending light around them. Wow! These applications are still largely theoretical. The potential for metamaterials to revolutionize optics and imaging is undeniable. Moreover, advances in computational imaging are blurring the lines between what we can see and what we can infer. Techniques like structured illumination microscopy use carefully patterned light to illuminate a sample, capturing multiple images that are then computationally processed to create a high-resolution image. This allows us to overcome the limitations of traditional microscopes, revealing details that would otherwise be blurred by diffraction. Similarly, techniques like compressive sensing can reconstruct images from far fewer measurements than traditional methods, enabling faster and more efficient imaging. Looking further ahead, the future of vision technology may lie in integrating these different approaches. Imagine a device that combines thermal imaging, terahertz imaging, quantum imaging, and computational imaging into a single, compact unit. This device could adaptively switch between different imaging modalities depending on the environment and the task at hand, providing us with an unprecedented ability to see the world around us, regardless of lighting conditions or obstacles. These technologies not only enhance our ability to perceive the world, but also fundamentally alter our understanding of it. They allow us to see the invisible, to probe the hidden, and to unravel the mysteries of the universe with ever-increasing precision. And it's not just about seeing better. It's about understanding better. The ability to visualize phenomena that were previously invisible opens up new avenues for scientific discovery, technological innovation, and artistic expression. And let's not forget the ethical implications. As our ability to see in the dark and through obstacles improves, we must also consider the potential for misuse. Technologies like terahertz imaging raise concerns about privacy and security. And it's crucial that we develop appropriate regulations to ensure that these technologies are used responsibly. The power to see comes with the responsibility to protect. So, as we continue to push the boundaries of vision technology, let's remember that our ultimate goal is not just to see more, but to see better. To see with greater clarity, greater understanding, and greater compassion. To use our enhanced vision to build a better future for ourselves and for the planet. The dance of light and darkness continues. And with these new technologies, we're poised to become more perceptive dancers than ever before. And now, let's broaden our perspective, zooming out from our pale blue dot to consider the grander implications of light and darkness in the search for extraterrestrial life. Because, perhaps paradoxically, both illumination and obscurity play crucial roles in our quest to answer the age-old question, are we alone? Our primary method for detecting potentially habitable planets and even technological civilizations is, of course, through light. We analyze the starlight that passes through a planet's atmosphere, looking for telltale signs of elements like oxygen or methane, biosignatures that could indicate the presence of life. We scan the skies for artificial light sources, city lights blazing on a distant world, a testament to an advanced civilization. We even listen for radio signals, deliberate broadcasts sent out into the cosmos in the hopes of making contact. All of these methods rely on detecting electromagnetic radiation, on intercepting the light in its various forms that emanates from other worlds. Think of it, we are essentially eavesdropping on the universe, tuning our instruments to the faint whispers of light traveling across vast interstellar distances. It's an incredibly ambitious endeavor, a testament to our curiosity and our unwavering belief that we are not alone. The universe is awash in electromagnetic radiation from the cosmic microwave background, the afterglow of the Big Bang, to the emissions from pulsars, quasars, and countless other celestial objects. Sifting through this cosmic static to find a faint, artificial signal is like trying to find a single drop of water in the ocean. And that's where darkness comes in. Because while light is our primary tool for detection, darkness may be the key to understanding the motivations and even the survival strategies of advanced extraterrestrial civilizations. Consider this: any sufficiently advanced civilization is likely to be aware of the risks inherent in broadcasting its existence to the universe. The dark forest theory, which we touched upon earlier, proposes that the cosmos is a dangerous place teeming with potentially hostile civilizations. In this scenario, the best strategy for survival is to remain silent, to avoid drawing attention to oneself. But how could a civilization actively minimize its electromagnetic footprint? How could it cloak itself in darkness, becoming invisible to potential adversaries? One possibility is that they might develop technologies to shield their planet from detection, either by absorbing or deflecting electromagnetic radiation. This could involve creating a massive planetary shield, a kind of Dyson sphere in reverse, designed to block all outgoing signals. Or perhaps they might use advanced camouflage techniques, manipulating their atmosphere to mask any artificial biosignature. Another possibility is that they might simply choose to limit their emissions. They might rely on localized communication networks, minimizing the amount of electromagnetic radiation that escapes their planet. They might develop highly efficient energy sources that don't produce excessive amounts of waste heat. Or they might simply choose to live in a more sustainable way, reducing their overall consumption and minimizing their impact on the environment. In effect, they might choose to embrace a kind of dark ecology, minimizing their presence in the universe and blending in with the natural background radiation. This wouldn't necessarily mean that they are technologically backward. On the contrary, it might require an incredibly advanced level of technology to achieve such a high degree of stealth. So, when we search for extraterrestrial life, perhaps we should be looking not just for the brightest and most obvious signals, but also for the absence of signals. We should be looking for planets that appear strangely quiet, planets that seem to be deliberately hiding from the rest of the universe. Of course, this is an incredibly difficult task. How do you prove the absence of something? How do you distinguish between a civilization that is actively hiding and a planet that is simply uninhabited? One approach is to look for anomalies, for patterns that don't quite fit with our understanding of natural phenomena. For example, if we detect a planet that has an atmosphere that is suspiciously devoid of certain elements, or if we observe a star system that is emitting an unusually low amount of electromagnetic radiation, this could be a sign that something is amiss. Another approach is to look for indirect evidence of advanced technology. For example, we might detect artificial structures on the surface of a planet, even if they are not emitting any detectable signals. Or we might observe unusual patterns of energy consumption, suggesting that a civilization is using advanced technologies to harness the power of its star. Ultimately, a search for extraterrestrial life is a complex and multifaceted endeavor. It requires us to be open to all possibilities, to consider both the light and the darkness, the signals and the silences. It requires us to challenge our assumptions about what life might be like on other worlds, and to be prepared for the unexpected, perhaps. The greatest challenge is to overcome our own biases. We tend to assume that any advanced civilization would be eager to communicate with us, to share its knowledge and its experiences. But this may not be the case. It's possible that other civilizations have learned from experience that it's best to remain silent, to avoid the attention of potentially hostile forces. It's also possible that they simply have different priorities than we do. They may be more interested in exploring their own inner worlds, in developing their own unique cultures, than in reaching out to other civilizations. Whatever the reason, we need to be prepared for the possibility that we may never find any evidence of extraterrestrial life. But that doesn't mean we should stop searching. The search itself is a valuable endeavor, forcing us to confront our own limitations and to expand our understanding of the universe and our place within it. And who knows, perhaps one day we will stumble upon a signal, a faint whisper from a distant world that will change everything. Or perhaps we will discover a planet shrouded in darkness, a testament to the wisdom and the resilience of a civilization that has chosen to remain hidden. Either way, the journey will be worth it. For in the end, the search for extraterrestrial life is not just about finding other civilizations. It's about understanding ourselves, about exploring the depths of our own potential, and about embracing the infinite possibilities of the universe. And that, my friends, is a journey worth taking, no matter where it leads us. And so, our journey through the realms of light and darkness draws to a close. We've explored the nature of light, its incredible speed, and how it shapes our perception of reality. We've delved into the seeming nothingness of darkness, understanding it not as an entity, but as the profound absence that allows light to shine even brighter. We've danced with the concepts, chasing photons and embracing the shadows they cast. Perhaps, in our exploration, we've come to realize that light and darkness are not opposing forces locked in an eternal struggle, but rather two sides of the same cosmic coin. They are interdependent, each defining and enhancing the other. Just as a painter needs both light and shadow to create depth and dimension on a canvas, the universe needs both light and darkness to weave its grand tapestry. Think about it. Without darkness, there could be no contrast, no form, no appreciation for the brilliance of a single star in the night sky. Without light, there could be no life, no warmth, no understanding of the universe we inhabit. It's this delicate balance, this constant interplay, that makes existence so rich and so profoundly beautiful. We, as human beings, are also part of this dance. We experience our own internal lights and shadows, moments of joy and sorrow, clarity and confusion, hope and despair. It's tempting to chase only the light, to shy away from the darkness within ourselves and in the world around us. But perhaps true wisdom lies in embracing both. For it is in the darkness that we often find the space for introspection, for growth, for understanding. It is in the quiet stillness of a dark night that we can hear the whispers of our own intuition, the murmurings of our deepest selves. It is in facing our fears and uncertainties, the shadows that lurk within, that we discover our own resilience, our own strength, our own inner light. And what of the vast, unknowable darkness that surrounds us? The mysteries of dark matter and dark energy, the unfathomable depths of black holes, the silent expanse of the cosmos beyond our reach. It's natural to feel a sense of unease, even fear, when confronted with such profound uncertainty. We are, after all, creatures who crave understanding, who seek to categorize and explain everything we encounter. But perhaps there is a certain peace to be found in accepting the unknown, in acknowledging that there are questions we may never answer, mysteries we may never unravel. In surrendering to the vastness of the cosmos, we can release our need for control and find a sense of awe and wonder that transcends our limited human understanding. Think of the early explorers venturing into uncharted territories, sailing into the unknown with only the stars to guide them. They faced countless dangers, uncertainties, and fears. Yet they persevered, driven by a thirst for knowledge and a willingness to embrace the unknown. And in doing so, They expanded our understanding of the world and our place within it. We are all explorers in our own way, navigating the uncharted territories of our lives, venturing into the unknown with each new day. And just like those early explorers, we can find strength and courage in embracing the darkness, in accepting the uncertainties that lie ahead. Let us not fear the shadows, but rather see them as an invitation to explore the hidden corners of our own minds and the vast mysteries of the universe. Let us not shy away from the unknown, but rather embrace it as an opportunity for growth and discovery. For in the dance of light and darkness, in the acceptance of both the known and the unknown, lies the path to true understanding, to lasting peace, and to a deeper appreciation for the beauty and wonder of existence. Let the knowledge that light has a speed, but darkness doesn't, serve as a constant reminder that sometimes the most profound discoveries are made not in the relentless pursuit of light, but in the quiet contemplation of the shadows. So go forth, embrace the dance, and find your own peace in the unknown. The universe awaits.